This video is brought to you by Onshape. Try the professional plan for free for up to 6 months with the link in the description. After spending 7 days in orbit around the Earth, the Space Shuttle orbiter now has arguably the most difficult portion of its mission to complete. A hell-blazing journey through the Earth's upper atmosphere, where it will travel so fast that it will rip air molecules apart, forming a layer of superheated plasma around the aircraft. Re-entry is where the Space Shuttle truly became a one-of-a-kind spacecraft. The Space Shuttle was a radical new idea, a spacecraft capable of not only surviving the immense heat of re-entry, but capable of transitioning to aerodynamic flight, which required careful molding of its wings and tail, balancing the needs of an unpowered glider with the needs of a re-entry vehicle. This is the insane engineering of re-entry. The re-entry procedure begins with a 2 to 4 minute burn of the orbital maneuvering engines, while the spacecraft is upside down and travelling backwards. With an orbital speed of around 7 km per second, the OMS pods need to reduce the orbiter's speed by just 0.1 km per second, 1.3% of its velocity, to lower its orbit enough to bring it into a collision course with the Earth's upper atmosphere. A precise manoeuvre will lead to little speed, and the orbiter will overshoot its narrow window for success, skimming through the thin upper atmosphere and potentially bounce back into space. The orbiter has wings that generate lift, after all. Bleed too much speed, and the orbiter will descend through the atmosphere too fast, reaching the thick lower atmosphere before enough speed has been leached away, resulting in catastrophic overheating. This narrow entry window was called the entry flight corridor. Once the delicate retro-firing sequence has been completed, the next phase of re-entry begins. The reaction control system flips the shuttle around and places it into a 40-degree upwards pitch angle, ready to meet the Earth's atmosphere, entering the upper atmosphere at 30 times the speed of sound. The speed is so great it begins to rip air molecules apart, creating a glowing cloud of charged plasma around the lower surface of the orbiter, with peak temperatures reaching 1,650 degrees Celsius. Nothing like this had ever been attempted. A blunt body capsule, like every other re-entry capsule to date, designed purely for thermal protection, is an engineering challenge. But tack on the needs of an aircraft, and the task gets vastly more difficult. Thankfully, NASA had a test run in 1959 with the X-15, the fastest plane in the history of humankind, and it advanced our understanding of hypersonic flight, providing many lessons that were incorporated into the Space Shuttle's design. However, the X-15 had one major advantage over the Space Shuttle. It didn't need to launch itself into orbit. It didn't even launch from the ground, instead launching from the belly of a B-52. This allowed the X-15 to use a state-of-the-art advanced heat-resistant aerospace metal, Inconel X, with a max operating temperature of 980 degrees Celsius. The Space Shuttle could not use this metal. Inconel X is too heavy, about 180% heavier than an equivalent aluminium airframe, a massive issue for an aircraft designed to be carried to orbit. The Space Shuttle's airframe, therefore, is not made from Inconel X. It is composed of lightweight aluminium, which has a max operating temperature of just 177 degrees, 5 times lower than Inconel X. The orbiter would experience temperatures 10 times greater than this for extended periods of its re-entry flight. To make matters worse, one of the principal lessons learned during the X-15 program was that the hot pink foam ablative coating sprayed onto the plane for the top speed flights was completely unusable for the Space Shuttle. An ablative coating is a sacrificial material designed to gradually burn and fall away from the aircraft, pulling the heat with it. However, the ablative coating of the X-15 had a nasty habit of burning away from the nose of the plane and begin attaching itself to the cockpit windows, rendering the pilots completely blind, which presented a bit of a problem. At one point, the engineers of the X-15 considered attaching small explosives to the window and intentionally exploding the outer pane of glass to remove the ablative stained window, leaving only the inner pane for landing. Thankfully, they came up with a much less risky solution of installing a mechanical eyelid to the left window that remained closed until the high-speed portion of the flight concluded, providing the pilot one clean window to land with. an extremely primitive solution that created stability issues, as the open eyelid acted like a canard, causing the plane to pitch up, roll right, and yaw right. Even more terrifying, this coating became explosive when mixed with the liquid oxygen and could be triggered by even a slight impact. A massive safety concern for a plane that required a liquid oxygen oxidizer to operate. A danger that would be multiplied manifold with a vehicle filled with 500,000 litres of liquid oxygen. The ablative was also not reusable, which would drastically increase the cost of refurbishing the shuttle between flights. The space shuttle would need to be better. As the space shuttle descended through the atmosphere, its nose and wings bore the brunt of the re-entry heat. The high-pressure shockwaves forming around them have created a layer of superheated plasma. If this heat managed to find its way into the delicate aluminium framework inside the orbiter, it would be game over. This is exactly what happened to the Columbia shuttle as a result of damage to the leading edge of these wings. The first step in protecting the orbiter's surface was to keep this superheated plasma as far away from the surface as possible. The nose, wings, and belly of the orbiter was carefully crafted to ensure shockwaves were kept at bay. We can see how using Schlerin imaging. A pointed missile-like vehicle pierces through the air with efficiency, and in doing so creates a shockwave, attached to its nose with an angle determined by its Mach number. This shockwave is simply a region of incredibly high pressure, and with that pressure comes incredibly high temperatures. This can have disastrous effects, as DARPA experienced twice in 2010 and 2011 when testing their sharp-nosed hypersonic re-entry vehicle, the HTV-2. Within 9 minutes of re-entering Earth's atmosphere, both vehicles disintegrated as a result of the 1,900-degree heat penetrating their metallic skin. The HTV-2 completed its mission of collecting hypersonic flight data, but the space shuttle needed to not only survive this mode of flight, but to do it repeatedly with minimal refurbishment. A good portion of this heat could be kept away from the aircraft skin with blunt-bodied design, which creates a rounded bow shockwave with a layer of insulating lower pressure air between the vehicle and the shockwave, reducing heat transfer. For this reason, the space shuttle's surface is carefully molded to take advantage of this phenomenon. The rounded nose cross-section gradually transitions to a blunted triangle. This shape minimized the heat reaching the less protected sidewall of the shuttle, which used lower temperature insulation. We are now 7 minutes into the re-entry procedure, having descended 50 kilometers in altitude, but only shedding 0.5 kilometers per second of our velocity. We've entered the period of maximum re-entry heat, a confluence of speed and atmospheric density. The layer of superheated plasma surrounding the shuttle is blocking communication to the computers and astronauts inside, a result of free electrons in the plasma interfering with electromagnetic communication techniques, a problem that would last for the next 12 minutes. For now, the shuttle is operating on its own telemetry data, ensuring that 40-degree angle of attack is maintained. Managing that angle with a velocity of 6.5 kilometers per second was no easy task. A massive control surface was needed. The elevons on the outer wing would not suffice. This is where the rear body flap came into play. It was a massive control surface underneath the shuttle's main engines, covered in high-temperature insulation. The body flap doubled as a heat shield for the shuttle's main engines. With no cooling liquid hydrogen running through the nozzles, the flap was needed to shield the engines from the heat of re-entry. On the Space Shuttle's third flight, the Kuiper Airborne Observatory flew underneath the orbiter as it re-entered and captured an infrared image of its searing hot belly, an experimental program to validate NASA's newly developed computational calculations and experimental testing. This is what it saw. The nose and leading edges are a scorching 1,500 degrees Celsius, far beyond what the aluminium airframe underneath is capable of enduring. These leading edges, experiencing the hottest temperatures, needed the most heat-resistant material on the entire shuttle, a reinforced carbon-carbon composite, one of the amazing materials created in the years between the development of the X-15 and the Space Shuttle. A carbon composite manufactured with a special post-processing step. It was initially manufactured like any other carbon fiber part, a carbon fiber weave molded into shape and bound together with a resin. However, the heat of re-entry would set the hydrocarbon resin on fire without special treatment. The post-processing step would solve this problem. The carbon composite is placed in a vacuum chamber and heated, causing the hydrocarbon resin to decompose, releasing the hydrogens, leaving layers of pure carbon behind, graphite. Carbon fibers bound together by a maze of graphite, strong and capable of withstanding 1,510 degrees Celsius. They face head-on into the inferno of hypersonic flight. The leading edge of the orbiter's wings is composed of 22 of these carbon-carbon panels, with sealing strips covering expansion gaps between each panel, an essential solution to a lesson hard won during the development of the X-15. To investigate the heat of hypersonic flight, the X-15 was painted with a special kind of paint that reacted to heat. And after one flight, the X-15 returned with strange, wedge-shaped patterns emanating from the leading edge expansion joints, small gaps in the leading edge to allow the Inconel skin to bend and contort with the wing without buckling. This localized heating was happening as a result of turbulent flow, increasing the rate of heat transfer to the metallic skin of the aircraft. To fix this, small floating strips of Inconel were placed over the expansion gaps. These strips of reinforced carbon-carbon serve the very same purpose. However, there is one more problem. Carbon is a thermally conductive material, not ideal for a heat shield. The space shuttle has been traveling through the atmosphere for 15 minutes, but is still traveling at 6 kilometers per second, and contact has not been re-established through the cloud of plasma surrounding the aircraft. This is a sustained heat, and with carbon being conductive, this heat could make its way to the aluminium airframe over this period of time. If these carbon-carbon shields were attached directly to the airframe, the heat would come in direct contact with the metal, raising it above its max operating temperature. To prevent this, the panels were fitted with Inconel attachment points that attach to the aluminium airframe with Inconel bolts. Inconel, being mostly made of steel, is a poor conductor of heat and could handle the heat the carbon parts transferred to it, without easily transferring that heat to the aluminium. This wasn't enough to protect the interior of the shuttle, however. A layer of insulating tiles were placed underneath the carbon-carbon shield too, the same insulation that was used on the underside of the entire orbiter. The Space Shuttle Columbia had 32,000 of these tiles, in 2 flavors, low temperature and high temperature, white and black. But both of these tiles were made from the same base material, silica fibers, just a few millimeters thick, which, by volume, made up just 10% of the tile. The remaining 90% was nothing but air, an excellent insulating material, a thick and light tile, composed of a material with a high operating temperature. The coating is where the tiles differ. The black tiles installed on the lower portion of the shuttle were covered in a black borosilicate and tetraboron silicide glass coating. This black coating helps dissipate heat before it can conduct to the vulnerable inner structure. Black for the same reason the SR-71 is black, Kirchhoff's rule of radiation. This rule tells us a good infrared heat absorber, basically anything black, is also an equally effective heat emitter. With the heat gained from hypersonic flight vastly higher than the heat gained from solar radiation, it's preferable to prioritize outward heat radiation than minimizing heat gained from solar radiation. So why isn't the entire space shuttle black like the SR-71? The space shuttle has one important difference with the SR-71. It exited Earth's atmosphere. Once outside the Earth's atmosphere, the intensity of solar radiation increases drastically. With the longest orbiter mission at 17 days, this heat had plenty of time to conduct through to the people inside. The orbiter did have huge radiator panels to reject heat to space, but to minimize their size, we want to reflect as much of that heat back into space, and for that reason, they are white. These tiles were coated with a similar glass coating, but with an aluminium oxide additive to provide the white coloring. The coatings also help to waterproof and strengthen these porous tiles. The tiles were assembled like a giant, precisely engineered puzzle with 32,000 pieces. Each tile assigned a serial number that corresponded to their location, shape, and thickness. The tiles were created by mixing cotton-like silica fibers with water. This mixture was then cast into large blocks and were then dried in a microwave oven. Once dried, they could be cut into smaller sheets. The tiles varied from 25mm to 127mm thick, with the 127mm tiles insulating up to 1280 degrees Celsius. These sheets were then cut into their precise shapes according to their assigned serial numbers, using a computer-controlled milling machine. We are now coming through to the end of the communication blackout, and enough of the heat of re-entry has reached the aluminium airframe to cause it to expand. A major problem, as these tiles are not flexible in the slightest and are quite fragile. The expanding airframe could easily break the tiles and open up a path for the superheated gas to penetrate inside. The engineers needed a way to allow the structure to move beneath the tiles without causing the tiles to pop off. To do this, the tiles were first glued in groups to a layer of flexible Nomex felt. This Nomex fabric allowed the structure beneath to flex, expanding the lower side of the felt without transferring that strain to the upper layer attached to the tiles. These tiles and felt were then attached to the shuttle using the same adhesive, a commercially available high-temperature RTV adhesive, a bright red silicone-based adhesive. To prevent collisions between tiles, gaps between 0.46mm and 1.9mm were included. Thankfully, the issue of turbulent flow created by expansion gaps primarily affected the leading edges of the wing, so these gaps were not covered on the exterior of the shuttle. In areas exposed to lesser temperatures, flexible heat shields were used, constructed from high-temperature silica and Nomex fibers to create a flexible fabric which were sewn together with the same fibers, giving a quilted blanket appearance, with the Nomex fabric capable of resisting temperatures up to 370 degrees, and the silica fabric capable of tolerating temperatures up to 650 degrees. These were lighter and easier to replace than the tiles, being bonded directly to the structure again with that bright red silicone RTV adhesive. We are now out of the communication blackout and approaching 4 km per second or Mach 12 in velocity, and are about 45 km in altitude, about 4 times the cruising altitude of an airliner. The orbiter has maintained that 40-degree angle of attack this entire time. Being forced to hold an angle of attack this large comes with some control problems. The orbiter needs to land precisely on a landing strip from orbit. Managing its trajectory while being stuck with its nose up would be difficult, especially for a glider with no way to add energy once it's been bled away by drag. If the space shuttle wanted to lower its lift and lower its altitude faster, it could not lower its angle of attack. So, the shuttle needed a special way to adjust its trajectory to adjust its landing area. Instead, the orbiter decreased its lift by banking. This split the lift into vertical and horizontal components, reducing the lift keeping the shuttle in the air and trading it for lift that moved it sideways. This is what a typical re-entry flight profile looked like. This line is the angle of attack, keeping steady until Mach 12, and then gradually reducing as it descends through the thick lower atmosphere. And this is the bank angle. As the orbiter crashes down from orbit, it banks wildly from side to side. The astronauts inside, who are already pointed 40 degrees up, are now tilted on their sides up to 70 degrees. The orbiter is essentially doing the fastest drift in history. There are some quirks to flying this high in the atmosphere at hypersonic speeds. The bank angle controls actually work in reverse to normal. If we deflect the right elevon down, it should increase lift on the right wing and cause that wing to rise, banking the aircraft anti-clockwise. But it doesn't. When the elevon is deflected downwards into the already compressed hypersonic air, it causes drag to rise on the outer wing. This causes the orbiter to turn its nose in that direction. As the nose turns in the direction of the deflected elevon, it shields that wing and causes a decrease in lift, causing the shuttle to bank in that direction. So, where a downwards deflecting elevon would typically cause an increase in lift on the wing, here, through a series of events, it causes a decrease in lift, working in reverse. Of course, this bank angle causes the orbiter to drift off target for its landing, and to correct, it needs to bank the other way. The orbiter has now slowed down to Mach 3, and at this point, the flight crew deploy air data sensors to aid in the final approach. 2 probes rotate from underneath the heat shield on either side of the nose, providing airspeed, angle of attack, and temperature data to the flight computer. At this point, the orbiter is flying like a plane. But it's not a plane, it's a glider, and the flight crew needed to carefully manage the remaining energy to land safely. especially as the orbiter was not built like a traditional glider. Balancing the need to survive re-entry while maximizing lift efficiency was a unique engineering challenge, made more difficult by Air Force funding, causing the design to skew closer to a plane than a re-entry vehicle. Early concepts of the shuttle drew inspiration from the X-15 with much smaller wings, more than enough to land the original smaller orbiter on a runway. The Air Force wanted a larger payload capacity, and they had one more specific requirement that required bigger wings. They wanted the space shuttle to be able to take off from Cape Canaveral, complete its mission, and land back at Cape Canaveral after a single orbit, essentially treating the space shuttle like a military operation to avoid Soviet attention, fast and elusive. This came with some issues. A single orbit took 90 minutes, in which time the Earth rotated below the shuttle's orbit by 2,000 kilometers. So, to return to its launch location, the orbiter would need to be capable of flying laterally by at least 2,000 kilometers. This is called cross range. The original X-15 inspired design was capable of just 370 kilometers of cross range. North American Rockwell proposed this huge blended body delta wing concept in 1970, which would have given the orbiter 2,800 kilometers of cross range. The fully reusable concept, with its crude booster rocket and internal fuel tanks, were not to be, but the large delta wings endured. These delta wings provided enough lift in both hypersonic, supersonic, and subsonic flight regimes to provide the cross range needed to reach the original launch site after a single orbit. Despite that, the space shuttle was an unwieldy aircraft, and with no powered flight, the commander had one shot to land it safely. So, they had to go through intensive training. In 1973, NASA created 4 training aircraft by modifying 4 Gulfstream jets to fly like the space shuttle. In order to mimic the immense drag the blunt body design of the space shuttle would create, the Gulfstreams flew with their landing gear down and their engines working in reverse, and flew with their flaps deflected upwards to decrease lift. With flight characteristics like this, the space shuttle needed to carefully manage its energy. Losing too much altitude far from the runway would be far from ideal. The pilots aim, guided by beacons and ground control, for a tangential entry into a circular approach path 5,800 meters in diameter just off the runway. The moment they intercept this circle, the space shuttle commences a deep spiraling turn. At this point, the space shuttle is still traveling at about 0.8 Mach, still very fast, and it's at this point the wings are stressed the most, hitting a higher max dynamic pressure than at any point during the re-entry process, due to the higher air pressure at this altitude. And the shuttle's descent rate increases, now losing altitude rapidly with the knowledge the runway is within a safe gliding distance, descending to about 3,000 meters in altitude and slowing to about 0.5 Mach. At this point, the shuttle enters a straight 20-degree down glide approach path, much steeper than any airliner approach path, bleeding speed as needed using the split rudder speed brake. The rudder on the vertical tail wasn't just used for controlling yaw by deflecting left and right. It could split in two, deflecting outwards to a maximum of 62 degrees on either side. The gear is lowered as late as possible, and in the final moments before touching down, the commander will increase the angle of attack of the shuttle using the elevons in order to slow its descent rate before touching down. At the moment of main gear touchdown, the speed brake is commanded to fully open. At this point, the shuttle is still traveling at 360 kilometers per hour, close to 0.3 Mach, and there is plenty of braking left to do. The runway at Cape Canaveral is 4.6 kilometers long, much longer than your average runway, with typical 3-kilometer long runways being able to deal with the heaviest of jumbo jets landing. As the nose gear touches down, the electro-hydraulic brakes in each of the 4 main landing gear wheels are fully engaged by application of the foot pedals in the cockpit. Each brake assembly had 9 carbon-lined beryllium discs, 4 rotors and 5 stators, which were pressed together to provide braking force. On STS-49, Bruce Melnick's mission, an additional braking mechanism was introduced, hidden away underneath the vertical tail speed brake, the drag chute. STS-49 was the maiden flight of both Endeavour and the drag chute, an explosively deployed parachute. You can even see the parachute door and sabot being flung from the back of the shuttle on landings. It was designed to allow the Space Shuttle to land on shorter 2,500-meter runways, a contingency plan in the event the Space Shuttle had to abort a launch and land on a runway on the other side of the Atlantic. For each and every launch, NASA sent staff to these predetermined landing locations, like Fairford RAF Base in Gloucestershire, England. A large team was needed to assist with the final moments of each Space Shuttle mission. And these teams were not once needed in the entire history of the Space Shuttle program. A giant fan was even rolled out on the runway to help disperse any toxic chemicals, like the hydrazine fuel, away from the shuttle and the crew. The mission is now over. The crew has disembarked and the Space Shuttle will be refurbished and flown back to Florida on the back of a 747 in preparation for its next mission. People often say how incredible it is that older aerospace and aviation projects like this were designed with pen and paper. Hand-drafted technical design was an art form, and a labor-intensive art form at that. Today, computer-aided design makes things vastly easier, like Onshape, today's sponsor. Onshape is available to try for free with the link in the description. Whether your company wants to evaluate a more modern cloud-based CAD system, or if you just need a design program for home 3D printing projects, Onshape is a fantastic option. Onshape is built entirely on the cloud, and because of that, Onshape users have some unique advantages. For example, engineers and designers are able to work together in Onshape at the same time on the same design across the globe, ensuring there is always a single source for your designs, a problem I had to contend with in my job as a design engineer, where sales reps kept sending out old, outdated files to clients. Onshape also runs in a browser, which means you can use it on virtually any device or operating system. Even highly computative intensive capabilities like finite element analysis and rendering are done completely in the cloud in Onshape, making the design process faster and easier than ever. If you or your company wants to test Onshape, engineers and product designers can get the Onshape Professional Plan for free for up to 6 months, and the base free plan is available for all for unlimited non-commercial use. You can sign up at onshape.pro/real engineering or by clicking the link in the description or on screen right now.